Good morning, everybody. I am Dr. S.S. Naidu, Assistant Professor in Mathematics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today we are going to discuss a very important topic in probability and statistics. It is mean, variance and mode of Poisson distribution. See, we have discussed earlier so many points about these mean, variance and mode of Poisson distribution. Especially this Poisson distribution is a special case of binomial distribution, and see both binomial distribution and Poisson distribution. These are the two types of distributions which are valid for discrete random variables. So in discrete random variable, there are two main types of distributions are there. They are binomial distribution and Poisson distribution. So especially this Poisson distribution is a limiting case of binomial distribution. So in binomial distribution, suppose if it become very large, then it will become a special case of normal distribution also. So this Poisson distribution also holds for larger values. If n tending to infinity, then we will take it will be a special case of binomial distribution, especially it comes as a Poisson distribution. So in Poisson distribution, the variable which is involved there is independent variable, and whatever variables you may involve in them, they will become independent variables. So for independent variables, if the distribution goes on exponentially, then it will come under a case of Poisson distribution. So in Poisson distribution, mean will be automatically equal to variance. Mean mu is automatically equal to variance sigma square. So that's why in this standard deviation is equal to plus or minus square root of mean. So same like that, mode also, how can we find by taking graph of that Poisson distribution, we can decide by counting its peaks of the graph, whether it is unimodal, bimodal, trimodal, multimodal. It will be decided by drawing the graph. So like that, we can discuss mean, variance and mode of Poisson distribution elaborately one by one like this. Let us see mean and variance of Poisson distribution. If mu is the average number, automatically you know mu is nothing but average of given things. It is mean or expected value. What does it mean? It is average number. So mu is the average number of successes occurring in a given time interval or region in the Poisson distribution. Then the mean and the variance of the Poisson distribution are both equal to mu. That is what we have discussed as a part of introduction. Thus, expected value, that is mean, nothing but mean. It is mu here, and variance v of x is equal to sigma square. It is also mu here, because in Poisson distribution both quantities are equal. Remember that in a Poisson distribution only one parameter mu is needed to determine the probability of any given event, because both are becoming equal. Now let us see the formula for Poisson distribution. Poisson distribution is actually an important type of probability distribution formula. As in the binomial distribution, we will not know the number of trials or the probability of success on a certain trial. So in a Poisson distribution, for a given random variable, for some x, it is e power minus lambda into lambda power x whole divided by x factorial. So this is the formula in Poisson distribution for the given rate of the parameter. We can find the required probability for the required situation. The average number of successes will be given for a certain time interval. The average number of successes is called lambda and denoted by the symbol Greek letter lambda. In this, we are going to discuss the Poisson distribution formula with some more examples. Now let us see concept of Poisson distribution. The French mathematician Simeon Denis Poisson developed this function in 1830. This is used to describe the number of times a gambler may win a rarely won game of chance out of a large number of trials. See, in attempting in a number of trials, each trial cannot be a success. So until he gets success, he attempts his trials. So in his consequence, in his sequential order of trials, at any for some xth trial, he may win. So this win comes for his exponential trials. That's why this gambler trial comes under Poisson distribution. The Poisson random variable follows the following conditions. So these conditions will be good for Poisson distribution for a Poisson variable. The number of successes into disjoint time intervals is independent. It is evident because one time interval is not dependent on other time interval. This time interval is different. This time interval is different. There is no connection. There is no joint. That's why they are disjoint. That's why they are independent to each other. That's why the number of successes into disjoint time intervals is independent. First property. Second one, the probability of success during a given small time interval is proportional to the entire length of the time interval. Why? Here, what the formula we have discussed just now, P of x is equal to some x, probability of some x is equal to e to the power minus lambda into lambda power x by x factorial. Here what we are telling, the probability of success during a given small time interval is proportional to the entire length of the time interval. Here see, let us take lambda is constant, time rate, outcome rate, it is constant, you cannot change. X, let us take it from 0, 1, 2, 3, 4, 5, etc. Then randomly, depending on x value, the probability values will come one by one. They will be proportional to proportional. That is the main concept and property of Poisson random variable. Besides the disjoint time intervals means there is no intersection. The Poisson random variable also applies to disjoint regions of space. Let us see some more applications of Poisson distribution. The number of deaths by horse kicking in the army of Russian. See, For here, one thing we have to understand: for every horse kicking, there should be no casualty of death. Some may be eventually or opportunistically they may survive. They need not be dead. So that's why in some cases death may occur. In some cases narrowly it may escape. That's why this chance occurs for a luckiest time of interval, luckiest time of trial. That's why this comes under Poisson distribution. This is also the main application and property of Poisson distribution. So the number of deaths by horse kicking in the army of Prussian means for every horse kicking there may not be a death. In some trials death may occur. In some cases they may survive. It depends upon the time interval, and at that time what happens, it depends upon that. Next, birth defects and genetic mutations. See, for one set of parents, suppose first trial may be some defect, and depending on that we cannot judge second, third births also for them, because of them will not be defect, cannot be defect. So second birth may be perfect, again third birth may be defect, fourth birth may be perfect. So it depends upon the genetic mutations. That's why this is also the main application of Poisson distribution. Next, let us see some rare diseases like leukemia, cancer type, because it is very infectious and so not independent, mainly in legal cases. Because in leukemia and some other dangerous diseases, and they are very much infectious also. See, they may not be independent in legal cases. Next, car accident prediction on roads. See, so in a very dirty roads, and the suppose there are so many holes on that road and it is muddy, some vehicles may go well, and suppose in some roads they are high standard roads and international level roads, and very severe accidents may occur there. So see, it depends upon time interval. See, sometimes rarely they may depend upon poor quality of roads, but here the time interval at that time happening plays a major role in Poisson distribution applications. So, if we see rare disease like leukemia, because it is very infectious and so not independent, mainly in legal cases. Car accident prediction on roads, we can see traffic flow and the ideal gap distance between vehicles plays an important role. The number of typing errors found on a page in a book, like that hairs found on McDonald's hamburgers, the spread of an endangered animal in Africa. It may not be even. In some areas, it may spread rapidly. In some areas, may not occur. It depends upon Poisson distribution flow. Failure of a machine in 1 month. See, for all machines, they may not fail in 1 month. Some machines, they may fail in 1.5 months. Some may fail in 2.5 months. So, it comes for a particular time interval, it may occur. So if we analyze this Poisson distribution formula for the probability distribution of a Poisson random variable, let us assume some x as a Poisson random variable. It is representing the number of successes occurring in a given time interval. Then that formula can be same formula whatever we have discussed earlier can be changed as p of x is equal to e to the power minus mu into mu to the power x by x factorial. Here what we have done, we have replaced lambda by mu. Why? This is Poisson distribution. In Poisson distribution what we have learnt? In Poisson distribution, the rate constant lambda is equal to mean is equal to variance. That's why in our formula we have replaced lambda with mu. Actually what is our formula? P of x is equal to e to the power minus lambda into lambda power x by x factorial. Here we are replacing lambda with mu. We are replacing lambda with mu because of this reason. So here x is equal to 0, 1, 2, 3, etc. E is equal to Euler constant, we know 2.718. Mu, mean number of successes in the given time interval or region of space. Now let us do some problems for proper application of this theoretical knowledge. Let us see one example. Some vehicles pass through a junction on a busy road at an average rate of 300 per hour. This 300 per hour is our lambda. Some vehicles pass through a junction on a busy road at an average rate of 300 per hour. So we have to take this 300 per hour is our outcome rate. It is a lambda. Now let us see, depending on that they are asking 3 questions. Find out the probability that none passes in a given minute. Second one, what is the expected number of passing in 2 minutes? Third question what they are asking is, find the probability that this expected number found above actually pass through in a given 2-minute period. Like that, 3 questions they are asking, we have to answer. For that, first we will compute the average number of cars per minute is 300 per hour. Here mu is equal to, mean is equal to 5. Now we are applying the formula probability for what is our actual formula? P of x is equal to e power minus mu into mu to the power x by x factorial. Just now we have discussed, apply and substitute these values in that. P of, instead of x we are using x naught is equal to e to the power minus, in place of mu we are placing 5 into mu to the power x, means 5 to the power x value 0 by x is 0 factorial. So it is 6.7379 into 10 power minus 3. Now, second question, what they are asking? Expected number each 2 minutes they are asking. So expected number is 5. For each 2 minutes means simply you have to multiply with 2. So it is 10. Next, third question, what they are asking? If for mu is equal to 10, replace it. P of x10 you find. So e power minus in place of mu, keep 10 into 10 to the power mu to the power x. Mu is 10, x is 10. So 10 to the power 10 by x factorial means 10 factorial. So after simplification it comes as 0.12511. So here, after discussing all these things, we can see how if a probability mass function graph depicts all these things. The Poisson distribution can be represented visually as a graph of the probability mass function. Why? Poisson distribution is nothing but what I have discussed here. In Poisson distribution, it is nothing but a exponential function. E to the power minus lambda into lambda power x by x factorial. It is growing exponentially. So that graph also, some bell-shaped graph we will get there, and in that how many number of peaks are there, that much number of modes will be there. That is the use of finding graph, drawing a graph. So a probability mass function is a function that describes a discrete probability distribution. The most probable number of events is represented by the peak, what we have discussed here. These number of peaks, let us count them. That number will give us the mode. When mu is a non-integer, the mode is the closest integer smaller than lambda. That we can see here. When lambda is an integer, there are two modes. They may be lambda and lambda minus 1. When lambda is low, the distribution is much longer on the right side of its peak than its left. That is what we are showing here. That is, it is strongly right skewed. See, here on x-axis we are taking the values of the random variable. On y-axis we are taking its probability. Here, for the values of x, it is depicting probability like this, like this, like this, and it never touches x-axis. It never touches x-axis, and it is strongly right-skewed graph. So it is depicting for two values, lambda and lambda minus 1. So, yes, previously I told you about a bell-shaped curve. So, this whenever this binomial distribution becomes larger, it comes as a normal distribution, and that normal distribution increases exponentially. It becomes a Poisson distribution. As lambda increases here, the distribution looks more and more similar to a normal distribution. In fact, when lambda is 10 or greater, a normal distribution is a good approximation of the Poisson distribution. Now let us discuss about mean and variance of Poisson distribution. Let us assume that a Poisson experiment in which the average number of successes within a given range is taken as lambda. In Poisson distribution, The mean of the distribution is represented by lambda, and E is a constant which is approximately equal to 2.71828, which is Euler's constant. Then the Poisson probability is P of x lambda is equal to e to the power minus lambda into lambda power x by x factorial. It is known to us. In Poisson distribution, the mean is represented as estimation of x is equal to lambda, because already we know about this. In Poisson distribution, the rate measure lambda is equal to mean value, and it is also equal to variance. In this case only, in Poisson distribution also only, not for all. In Poisson distribution only, it holds good. Lambda is equal to mean is equal to variance. So it means that expected value of x means C of x, it is mean. It is equal to variance of x. That is here what we have discussed. It is nothing but this. So V of x is the variance. Let us see one example for a better understanding. A random variable x has a Poisson distribution with a parameter lambda such that P of x is equal to 1 is equal to 0.2 times P of x is equal to 2. So, one relation is given here. It is the relation which gives for P of x is equal to 1 and P of x is equal to 2. P of x is equal to 1 is 0.2 times P of x is equal to 2. One relation is given in the given sum. We have to use that relation and solve. Find probability of x is equal to 0. Here, whatever given using our definition, let us spread it out. For the Poisson distribution, the probability function defined as P of x is equal to some variable x is equal to e to the power minus lambda into lambda power x divided by x factorial is a formula, fundamental formula. Here lambda is a parameter. So given that, now we use that constant. What is given there? P of x is equal to 1 is equal to 0.2 times P of x is equal to 2. Apply formula and elaborate it. P of x is equal to 1 means apply formula e to the power minus lambda into lambda to the power x means 1 divided by x factorial means 1 factorial is equal to 0.2 times P of x is equal to means apply in formula e to the power minus lambda into lambda square divided by 2 factorial. So cancelling e power minus lambda on both sides, lambda is equal to lambda square by 10. So the lambda value will become 10. Lambda value will become 10. Now substitute lambda is equal to 10 in this formula. We get P of x is equal to 0. Now what we have got there, lambda is equal to 10. Now we have to get P of x is equal to 0. So is equal to apply formula e power minus lambda into lambda power x. Here this is the formula for general for P of x is equal to e power minus lambda into lambda power x by x factorial. Now we want P of x is equal to 0 is equal to e to the power minus lambda into lambda power 0 by x factorial 0. So it is P of here lambda value is 10. So it is e power minus 10 into lambda power 0 by 0 factorial. So p of x is equal to 0 is equal to lambda power 0 is 1, 0 factorial is 1. So its value is e power minus 10. It is nothing but 1 by e power 10. From your tables we can see e power 10 value also. So like that we can find p of x is equal to 0. Now let us see one more example. Telephone calls arrive at an exchange according to the Poisson process at a rate lambda is equal to 2 per minute. Calculate the probability that exactly 2 calls will be received during each of the first 5 minutes of the hour. Here x is equal to 5 we have to take, lambda is equal to 2 we have to take. Assume that capital N be the number of calls received during a 1 minute period. Therefore, P of N is equal to 2 is equal to, keep it in our formula, e power minus 2 into 2 square divided by 2 factorial. So simplification, after simplification it comes as 2 e power minus 2. P of N is equal to is 2 e power minus 2. Now some capital M be the number of minutes among 5 minutes considered during which exactly 2 calls will be received. Thus M follows a binomial distribution with parameters n is equal to 5 and p is equal to 2 e power minus 2. Now let us find p of m is equal to 5 is what? 2 to the power 5 is 32 into e to the power minus 10. So p of m is equal to 5 is equal to this value from tables. It will come as 0.00145, where e is a constant which is approximately equal to 2.718 Euler's constant. Now let us distinguish Poisson sampling and binomial sampling. When we were speaking of the Poisson distribution, we don't know how many calls there would be each day. In this case, n was a random variable. This is an important characteristic of the Poisson distribution. Suppose, however, that we modified our design to wait for 20 calls of various kinds to come in each day and tallied the number of calls out of 20 that related to sexual harassment. Here the sample size 20 is fixed rather than random, and the Poisson distribution does not apply. Now let us see Poisson and binomial multinomial models of contingency tables. The sampling plan that lies behind data collection can take on many different characteristics and affect the optimal model of the data. Optimal model of the data. The way in which we model data may affect the analysis we use. With the Poisson distribution, we know the mean mu, but not the sample size. Suppose to extend the example of sexual harassment, we sort the calls we receive into allegations of sexual harassment and allegations of other misbehaviors. We also sort the calls into those alleging infractions by co-workers and those alleging infractions by superiors, because the total sample size is a random, not a fixed variable. We could model the data by treating each of the 4 cell counts as independent Poisson variates. So let us see once again, as a recapitulation, let us distinguish Poisson and binomial sampling. In Poisson sampling, the main characteristic is the number n. The random variable n plays an important role. Suppose, however, that we modified our design to wait for, suppose for 20 calls of various kinds to come in each day, and tallied the number of calls out of 20 that related to some sexual harassment event. Here, the sample size 20 is fixed rather than random, and the Poisson distribution does not apply. Why? Because for every 20, it may happen or may not happen. That's why, well, in Poisson distribution, it is a little bit different from binomial sampling. In binomial sampling, continuity may be there, but in Poisson distribution, continuity, there is no surety of continuity in Poisson distribution. For a particular time of interval, it may happen. For other time interval, it may not happen. That is the main difference between binomial distribution and Poisson distribution. Thank you. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.